Hello, and welcome to this presentation, Getting the Most from Your Meter, which was originally presented at the 2016 Passaic River Symposium and is intended to help anyone with a water quality meter make more effective and reliable dissolved oxygen, conductivity, and pH measurements. So we're going to talk about the 10 commandments for effective meter use, how the dissolved oxygen meter works, how the conductivity and salinity are measured, and a little bit about measuring the pH. So let's begin with the 10 commandments for using your meter effectively. First and foremost, read the directions. Secondly, maintain your electrodes. All of the different types of electrodes, pH and dissolved oxygen in particular, have specific maintenance instructions. Make sure you understand these maintenance instructions so that you can keep your meter running effectively. And of course, you're going to read the directions. Never forget the importance of temperature. The amount of dissolved oxygen in water, the conductivity measurements, and even the pH are temperature dependent. So your meter will be equipped with a temperature sensor. Make sure that temperature sensor is working correctly if you want to get the most accurate measurements. And of course, read the directions. You should also calibrate your probes with the appropriate standards. We'll talk about the types of standards for each of these types of measurements: dissolved oxygen, conductivity, and pH. And read the directions. At the end of the day, make sure that you wash and store your probes properly. This will greatly extend their useful life. Frequently, particularly when people are working in brackish water or salt water, not cleaning the probes properly will result in them being heavily encrusted with salt and being damaged. So, at the end of the day, wash your probes with distilled water or deionized water and store them according to the directions, and you'll know how to do that because you're going to read the directions. You always want to keep extra batteries handy. Oh, and did I mention that you really should read the directions? So let's begin with dissolved oxygen measurements. Essentially, the dissolved oxygen in the water column, in the lake, in the river, in the ocean, in the estuary, represents the amount of oxygen that can be dissolved in the water such that the pressure of the oxygen in the air pushing down on the water is equal to the pressure of the oxygen dissolved in the water pushing up against the atmosphere. These two forces exist in equilibrium. Now, it takes less dissolved oxygen at higher temperatures to push against the atmospheric oxygen that is pushing down on the water surface, and it takes more dissolved oxygen to exert the same amount of pressure at a lower temperature. This is why hot liquids or warm liquids hold less dissolved gases in solution than do cold liquids. You'll frequently hear the phrase cold, clear, oxygen-rich waters to describe, for instance, the Arctic Ocean. So what are you going to see when you actually look at your dissolved oxygen sensor? The first thing you should notice is a permeable membrane at the bottom of the sensor and two metals or two metal electrodes inside a chamber that is filled with an electrolyte, potassium hydroxide in this example. There is a working electrode that is platinum, silver, or gold, and there is a counter electrode that is lead or aluminum. So how does a galvanic dissolved oxygen sensor work? The dissolved oxygen migrates through this permeable membrane into the electrolyte solution, in this case, again, potassium hydroxide. And at the working electrode, we add 4 electrons to the oxygen molecule. This is the dissolved oxygen molecule, and with some water reacts to produce 4 hydroxide ions. So we're adding electrons to the dissolved oxygen molecule, or we are reducing it, as the chemist would say. So where do those electrons come from? These electrons are drawn from the counter electrode. They pass through an amperage meter, and the current created by these moving electrons is measured by the amperage meter, which then is translated into a dissolved oxygen value. The polarographic dissolved oxygen sensor is very similar. It also has a permeable membrane. It has an electrolyte solution. It has a working and a counter electrode. But in addition to the amp meter, it also has a source of voltage. So how does a polarographic sensor work? In this case, we use our voltage source to apply a voltage to our working electrode where the oxygen is being reduced. Once again, to get the electrons that will make this reaction go, we draw them from the counter electrode and they pass through the amp meter. The current passing through the amperage meter is exactly proportional to the amount of oxygen that is being reduced at the working electrode. And here is the chemical reaction. Dissolved oxygen, again, that is transferred or migrated through this permeable membrane, plus 2 water molecules, plus 4 electrons give 4 hydroxide ions. Now, both of these electrochemical measurements consume oxygen. So eventually there'll be no more dissolved oxygen in the electrolyte solution, there'll be no more dissolved oxygen just outside of the membrane. So it's necessary to keep the sample stirring or to keep the probe gently swirling or gently moving in the water so that fresh dissolved oxygen is always available to migrate up through the membranes. Okay, so what? According to YSI, the galvanic sensors do not require a warm-up time. Essentially, they are always on. As long as there's dissolved oxygen, or as long as there is oxygen from the atmosphere, for instance, undergoing reduction at the working electrode, and as long as the counter electrode is still providing electrons, the reaction will go. So the reaction is already going on when you turn the meter on. They do not require a warm-up time. Polarographic, on the other hand, do require a warm-up time before use. Now, because galvanic sensors are continuously consuming the anode or the counter electrode, even when the instrument is turned off, these sensors will have a shorter theoretical life. The consumption of the counter electrode, the consumption of the counter electrode stops when the instrument is turned off in a polarographic system. Thus, they have a longer theoretical sensor life. Now, there's another option, and that is optical sensors. From the outside, these may look a lot like your electrochemical sensors, the galvanic and the polarographic. We have a permeable membrane, and dissolved oxygen migrates through that permeable membrane. The dissolved oxygen then binds to what's called a lumiphore. So let's look at the parts of this sensor. We have our permeable membrane and what's called a lumiphore. We shine light at the lumiphore. A blue light is shown at the lumiphore. The lumiphore then re-emits that light re-emits the energy in the form of red light. So blue light gets shown in and red light is emitted. Now, unfortunately, when the dissolved oxygen binds to the lumiphore, the chemical reaction that generates the red light is quenched. So the more blue light that comes in, the more dissolved oxygen, the less red light that comes back. And we can use that phenomena to measure the amount of oxygen that is bound to the lumiphore. There are a number of very good advantages to optical sensors. They require a lot less maintenance and can go for longer periods of time between their calibrations, although they may have a slightly longer response time. Most people I've spoken to said that they'll gladly trade the longer response time for much less maintenance. The dissolved oxygen optical sensors may require as much as 40 seconds per reading. Unfortunately, many regulatory agencies still do not completely accept this technology. Whatever kind of sensor you have, it is very important to know which maintenance kit you should need to buy. This is a YSI maintenance kit. You'll note that it is for a galvanic oxygen sensor. It has replacement membranes and it has replacement electrolyte solution. You'll fill this membrane cap combination unit with your electrolytic solution that you'll make up in this bottle and screw it on to the end of the probe to replace the membrane. It is very important to know what kind of sensor you have and what maintenance kit you need. You're going to frequently have to replace the membrane, and this is true of all types of sensors. This is true for polarographic, galvanic, luminescent sensors because the membranes can become clogged. For the electrochemical sensors, you will need to replace the filling solution or the electrolyte. And both of the working electrode and the counter electrode can be cleaned, usually with a very fine grit sandpaper. Whatever you do, read the directions so that you know how to replace the membrane, replace the filling solution, and clean the various electrodes. Now that we know how the meter works, how do we calibrate it? There are three main ways we calibrate a dissolved oxygen meter: with the Winkler titration, against air saturation, which is sometimes called the field calibration, and calibration against oxygen-saturated water, which we do in the laboratory. You should be running the calibration against the Winkler titration at least once a week, and calibration by air saturation or a field calibration at least once a day on the days you're using the meter. You may already be familiar with the Winkler titration. We take a sample of water with a certain amount of dissolved oxygen in it, add some chemicals to it, and convert the dissolved oxygen to another form and generate iodine in the process. We then titrate the iodine, and when all of the iodine is gone from the solution, we know how much dissolved oxygen was present. So let's look at the chemical reactions. We take our dissolved oxygen in the original sample, react it with manganese, and then react that with another material, and we'll generate the I3-1 ion, and this gives a yellow color. So if you run a Winkler titration, you may remember the yellow iodine color in the solution. We then react the iodine with sodium thiosulfate, and when the iodine ion here, the I3-1, has been consumed in this reaction, the solution turns clear. This Winkler titration is required weekly by the New Jersey Department of Environmental Protection, and they insist that the Winkler titration result and the dissolved oxygen result from your meter be within 0.3 parts per million of one another. Now, the important thing to remember about the Winkler titration is that the amount of I3-1 that is produced is exactly proportional to the amount of oxygen in the original sample. I'll say this again. This yellow-colored I3-1 is exactly proportioned to the amount of oxygen in the original sample. So if we know how much sodium thiosulfate is required to remove this from solution, we know how much dissolved oxygen was in the original solution. This makes it extremely accurate and highly reliable. But the key to a good Winkler titration is having fresh reagents. So make sure when you buy reagents for your Winkler titration, you check the expiration dates carefully. And please don't ask me how I know that. These are the reagents that I prefer, which are sold by the Lamont Company. You can buy the thiosulfate titrant. You could buy the chemicals to convert the dissolved oxygen to an insoluble form and generate the iodine. The acid that is required to make the reaction go is provided, and it also comes with a sample bottle. Now let's talk about the field calibration, and this should be done at least once a day, every day you are working in the field. So let's begin by talking about the oxygen in the atmosphere. Let me ask you, what percentage of the oxygen in the atmosphere is oxygen? That's a strange question, but I'll ask it again. What percentage of the oxygen in the atmosphere is oxygen? And the answer, obviously, is 100%. So we say that the atmospheric air is 100% oxygen saturated. You cannot have more than 100% oxygen in the atmospheric. You cannot have more than 100% of the oxygen in the atmosphere as oxygen. So what we do is we put the sensor in the atmosphere. The atmospheric oxygen forces its way through the membrane. And again, we say that the oxygen is 100% saturated. So when the oxygen from the air is forcing its way through the membrane, we know that the percent saturation is 100%. The oxygen, there cannot be any more oxygen than there is in the atmosphere. Now, the advantage of this field calibration is that it's very easy to do in the field. If you find your readings seem to be drifting, you can just put your meter back in the calibrate mode and redo the air calibration or the field calibration. The disadvantage of this is that you must know the barometric pressure or your altitude above sea level. You have to know how much air pressure is pushing the oxygen through the membrane so that it can react with your sensor. And you'll know how to do that because you will read the directions. All of the field meter directions will tell you how to do an air calibration or calibration against in the field. Excuse me. I want to talk a little bit about this idea of saturation. Oxygen will dissolve in water at a certain concentration, usually expressed in parts per million or milligrams per liter, and that will vary with temperature. Now remember, I said a few slides ago that the amount of oxygen in the water is exerting an equal force against the oxygen in the atmosphere so that these two exist in equilibrium. When the water is warm, the oxygen molecules are much more energetic, and it takes far less of them to exert the same pressure as the oxygen in the air. When the oxygen in the water and the oxygen in the air are exactly in equilibrium, we say that the water is saturated. So that at about 5-7 degrees Celsius, there cannot be more than 12 parts per million of dissolved oxygen in the water. It takes 12 milligrams of oxygen per liter to exert the pressure against the atmosphere. Whereas up here at around 26 or 27 degrees centigrade, it only takes about 8 milligrams of oxygen per liter to exert the same amount of pressure. Most of the water temperatures that we'll be measuring, somewhere around 20 degrees or 25 degrees, will have somewhere between 7 and 8 parts per million oxygen or 7 to 8 milligrams of oxygen per liter pushing up against the air and keeping the oxygen in the water and the oxygen in the air in equilibrium. You can think of oxygen saturation in water as at a certain temperature, the water simply cannot hold any more oxygen. Under normal circumstances, there are such things as supersaturated, but that's a lesson for another day. Now, how do we calibrate against air or against oxygen-saturated water in the laboratory? This is a very good way to check your meter, and it is very reliable. So what you're going to do is you're going to have a bucket of tap water, not distilled water, but tap water. And into that bucket of tap water, you're going to bubble a stream of air, and that will cause the oxygen in the air to become dissolved in the water. At about 20 degrees centigrade, the saturation of oxygen in the water is about 9.2 milligrams per liter or parts per million. It may take up to 4 hours to completely saturate the water, but once you have saturated the water, all you need to know is the water temperature, and you'll know how much dissolved oxygen is present in the water. Incidentally, if you're going to do a Winkler titration, it's always a good idea to keep this stirring to make sure that the dissolved oxygen is evenly distributed throughout the bucket of tap water. We can also remove the dissolved oxygen using sodium sulfide, about 2 grams per liter, and add a small pinch of cobalt chloride to serve as a catalyst. The sodium sulfide will completely remove all of the dissolved oxygen from the water, and your meter should read 0 parts per million dissolved oxygen, or at the very least less than 0.3 parts per million. Sodium sulfide used to be added to water supplies for steam boilers to remove oxygen because the presence of oxygen in the water supply might cause the steam boilers to rust. This is a good way to test your meter to make sure that it is working at low concentrations of oxygen, and this procedure is also required by the New Jersey Department of Environmental Protection. We'll begin conductivity and salinity in our next video. Thank you,